In this video here, we're going to take a look at three-dimensional problems with objects moving in horizontal circles. That's probably the longest title here for any A-Level Further Maths video, but there we go. So what does this video entail then? So in this video here, we're going to discover how the method of resolving forces can be used to solve a problem about an object moving in a horizontal circle. And before continuing with this video here, please just make sure then that you're confident with the previous material within this chapter. So just go back and watch the previous videos, right? If you're not confident with the previous material, then you are going to find this video more challenging. Clearly, the concepts in this video here build on the previous concepts that we've introduced in this chapter, right? So I'm hoping that's kind of obvious and I shouldn't really need to repeat that. But again, just go back and watch the previous material if you're not too confident. So I think the best way to really demonstrate this concept here, in terms of the theory, there's not too much to it. I think the best way to really demonstrate this here then is just work through a practice question together. So let's not waste any more time then, and let's just get started with this practice question. All right, so let's just get started then with the one practice question for this video. So what do we have then for this question here? So what we've got then is a particle of mass 4 kg that's attached to one end of a light inextensible string of length 50 centimeters. We're then told that the other end of the string is attached to a fixed point A, and the particle moves with constant angular speed in a horizontal circle of radius 40 centimeters. So we're then also told here that the center of the circle is vertically below A, and all we want to do here then is just calculate the tension in the string and also find the angular speed of the particle. Right, so first things first here, we don't have a diagram. And again, for most further mechanics 2 problems here, if we do not have a diagram, then basically just start by drawing a quick diagram. Because what we're going to need to do here is resolve forces, right? So without a diagram, that is pretty tricky to see for most students anyway, and I do think it's asking for trouble. So just take the extra 30 seconds to a minute here just to draw a quick diagram, right? Now what I'll actually do here is I'll just draw 2 diagrams, right? The first one, I'll just kind of show you what's actually happening with this problem, and then the second one will allow us to resolve the forces here. So what I've got then here is a particle that's moving around a circle, right? And what we've got here is a fixed point somewhere up here, right? So this fixed point here is the fixed point A. So I'll denote that here as A. Now, around this point here, okay, this is the center of the circle. So what I've got here is a circle. Now, apologies because if you've watched any of my videos before, you'll know my art skills are certainly not the best. But basically what I've got here then is this. Okay, so I've got my fixed point here, and attached to the fixed point then we have some string, right? That goes to a point here on the circumference of the circle, right? Okay, and this here then is our particle. So what I've got here is the radius. Now, I'm not going to add the relevant forces to this diagram here just because it's going to be extremely messy and I don't have a whole lot of room. But basically what's going to happen here then is this particle will move around this circular path, right? If I do that in a different color, then it's going to go around the circular path, something like this, okay? I've got an angle here. So I'll let this angle here, this angle of inclination be theta, okay? And I'll also have a tension here in the string again, where this string is 50 centimeters. So I'll just add the tension here. We have a tension force in the string, just like that. Now, again, like I just said, I'm not going to add the forces to this diagram here, other than the tension. What I'll also do here then, as I just said, right, is actually just draw a force diagram, okay? So this diagram here isn't really necessary for, answering an exam style question, just like this one. But basically what I want to do here is just show you visually what's actually happening, right? So now for the force diagram here, well, we've just simply got a right angle triangle. So something like this. Clearly, these should be straight lines. It's not perfect, but you get the idea, right? So I've got my right angle here, like so. We've got this angle here, which we've just denoted as theta. That is the angle of inclination here. So we've got theta there. As we've already mentioned, we have a tension force here in the string. This point here is A. At this point here, that's where we had the particle, right? So we had the particle here. Now, with the particle, we do have the weight force to account for. So what is the mass here? So the particle has a mass of 4 kg. So the weight force then is 4 g newtons acting vertically downwards, right? So I've got 4g newtons acting vertically downwards, just like that. What else are we missing here? So I've got the lengths here. So the string here is 50 centimeters. Now, I don't want to write this in centimeters. I want to give this in meters here. So 50 centimeters in meters is 0.5 meters, right? 0.5 meters. What we're also told here is the circle has a radius of 40 centimeters. So again, rather than giving this in centimeters here, we're just going to give this in meters. So 0.4 meters there. Are we missing anything else? What else do we need here? Oh, we also want the acceleration, right? So the acceleration here is going to be going towards the circle. And this would just be, in this case here, 0.4 omega squared. Okay, it's going to be r omega squared, but r here is 0.4. So 0.4 omega squared. Okay, and that here gives us the acceleration. I think at this point here, that gives us a complete diagram. If we are missing anything, then clearly we can just come back to the relevant diagram a little bit later on. But for now, that should do here. So what I'll do here then is I'll just let T be the tension in the string. I've already kind of denoted that here anyway, but I'll just state it here. So let T be the tension in the string. Let T be the tension in the string. And what I'll also do here is let omega be the angular speed. We let T be the tension in the string and omega be the angular speed. Now this symbol here, that is supposed to be omega. My omega symbols are never the best, but hopefully you can just about follow along there with my writing. Perfect. So what we're going to do here then. So what we're going to do here is just start then by resolving vertically. Okay. So I'm going to resolve vertically here, taking upwards as positive. So resolving vertically here, taking upwards as positive. So what do we get here then? So forces acting up here, well, in this case here, because the angle is between the string and the horizontal here, this would be T sine theta, right? So it's T sine of whatever this angle is here. So, as we've just said, then we get T sine theta. Just as a quick note here, if this angle was here between the string and the vertical, then this would be T cos theta, right? But in this case here, because the angle is between the horizontal and the string, then in this case here, once we resolve into components, we get T sine theta, right? So force acting upwards is just simply T sine theta. There's no vertical acceleration here, right? So I don't need to account for that. So in this case here, forces acting up equal forces acting down. Well, in this case here, the only force acting down then is over G, right? So T sine theta equals over G. Perfect. So we've resolved vertically there. Now let's just resolve horizontally. So what I'll do here is I will take towards the center here as positive, right? So resolving not to the left as such, but kind of denoting that's an arrow here. It's to the left, right, but to the center of the circle here. So again, what do I get here? So to the center then, I'm just going to get T cos theta now. We get T cos theta. Obviously, again, if the angle was here between the vertical and the string, then this would be T sine theta, right? But again, the angle's here. So we get T cos theta once we resolve this here into components. Now we do have acceleration here horizontally to account for. So using F equals ma, right? Newton's second law here. So let's make a note then. Using F equals ma. So this is F here. That's now equal to m times a. So the mass here is 4. We then times this by the acceleration, and the acceleration here is 0.4 omega squared, right? So I've got 4 times then 0.4 omega squared. Perfect. Okay. What I'll do here is I'll call this equation 1, and we'll call this here equation 2. Perfect. Let's just keep going then. Now, What you should hopefully recognize here is we have a 3, 4, 5 triangle, right? This here is 0.4 meters. This here is 0.5 meters. So what that means then is this length here, the height, that must be 0.3 meters, right? So we have a 3, 4, 5 triangle. Just make a quick note here. So we have a 3, 4, 5 triangle. So in that case then, for sine theta here, so sine theta here, that would be equal to 3/5, right? Just basic trigonometric ratios. And then for cos theta here, cos theta is equal to 4/5, right? We don't need to worry about tan theta here, right? We just got sine theta and cos theta, so that's absolutely fine here. So going back to equation 1 then, what I want to do here, as the question asks for, is calculate the tension in the string. Now, given that we know that sine theta is just simply 3/5, we can now easily find the tension in the string, right? So therefore then, T here, just not just resolving, rearranging, there we go, English is hard. Rearranging here for T, right, I just simply get 4g over sine theta. So T is equal to 4g all over sine theta. As we've just said then, sine theta here is 3/5, right? So I get 4 times 9.8, and that's all over 3/5. So this is just the same then as 20 times 9.8 over 3. So 20 times 9.8 over 3. Just put this into your calculator, right? And what you should get here then is 196 over 3. So I get 196 over 3 newtons there, or alternatively, what you can do here is just give this as a decimal. So let's quickly grab my calculator here. What does that give me then? So 196 over 3. So to one decimal place, then I get 65.3 newtons there. Okay, so 65.3 newtons there. Perfect. Okay. Now just be careful, then we're not done here. So what I've just stated there is the tension in the string. But don't forget, then we do also need the angular speed of the particle, right? So for the angular speed here, we just go back to equation 2. So to finish with then, let's just do that up here. So going to equation 2 here, what we need to do then is just rearrange, right, and make omega squared the subject. And from there then, we can just take the square root of both sides. So omega squared is equal to, so we get T cos theta is, not equal to, all over, I'm struggling today. So it's all over 4 times 0.4, right? So 4 times 0.4 is just 1.6, right? So I get T cos theta over 1.6 here. Now cos theta, that is 4/5. So we also know T as well. So T here is 196 over 3. So let's just substitute in everything here into omega squared. So I've got T, which is 196 over 3. For now, I'm just going to keep everything in exact form, just to make my life a little bit easier. Times that by cos theta, which is 4/5. We times that by 4/5 here. And that's all over then 1.6 here. So just quickly throw this into your calculator here. And if you do that correctly, then what you get here in exact form is 98 over 3. So I get 98 over 3 here, and this is for omega squared. Okay. Now, we don't want omega squared here. We just want the angular speed of the particle, right? So what I need to do here then is just simply take the square root of both sides here. So therefore then, omega here is the square root of 98 over 3. So this won't be, pretty result here. It's going to be a decimal. So to two significant figures then, what do we get here? What I simply get then is 5.7 here. So 5.7, and then don't forget your units here. We're looking at angular speed here. So the units then are radians per second, right? So rad second. Rad per second there. And there we go. So let me just quickly double check then. This here, I quickly did that off the top of my head. So 20 times 9.8, divide that by 3. Yeah, 196 over 3. Perfect. Just quick double checking that before I say everything is correct. And then it turns out that I've done it all incorrect. But there we go, right? Perfect. So as you can see then, these questions here aren't particularly tricky, but I do think a diagram is essential. Trying to solve a problem like this one without a diagram is definitely not recommended. Just take the extra couple of minutes here just to draw, a quick couple of diagrams. As you can see, again, it's nothing, it isn't anything too crazy. But there we go. So that gives us the solution here, or the, solution to the one practice question for this video. And that brings us to the end then of this video here. As you can see, it's a bit of a tongue twister on three-dimensional problems with objects moving in horizontal circles.